So first of all, I just want to thank the organizers for putting this together and bringing, I guess, this diverse group of people together. I'm Mike Pavlin. I'm in the operations group in the business school at Wilfrid Laurier University in Waterloo, Ontario. This is work that started here at the University of Chicago with John Burge and Ali Hortaxu. It's empirical work looking at using data to, from outcomes of markets to get back out the market structure. And I guess it continues in the somewhat of the same theme that we were left with yesterday with Ali's tutorial. And so I guess we'll have another empirical talk after this. So enjoy it. I won't go through the title. Rather than parsing that, I put together a little slide to say what the objectives are. There's two things I'm hoping you'll get out of this talk. One, we're going to introduce a method to recover that structure. By structure, what I'm talking about is sort of system-wide, in this case, transmission constraints, things that are restricting the flow of goods between areas, by taking a look at the prices. The methodology relies on markets being optimal or efficient in some way. Optimal, in this case, if we have an institutional market like an electricity market where we know the basically how the allocation mechanism is working, and we know that they're pricing based on dual values of that optimal allocation problem, then we can use that information to the theory of inverse optimization to back out how these prices are arrived at. So once we have that data, we're able to look at how that pricing mechanism worked in the first place, how the market was designed, I guess, and also look at the distribution of market power. Right? So we've got these transmission constraints which are interfering the flow. How does that impact how people in different parts of the grid or of the market footprint are able to operate? The second part is to look at a particular market design in electricity markets, which is something of a prerequisite to understanding the first part. So I'll present everything in the context of this electricity pricing mechanism, which is locational marginal pricing. And we'll look at actual applications in the MISO electricity market. So with that in mind, I'll start by looking at the Midcontinent ISO at this particular electricity market, what locational marginal pricing means there. So a little bit of tutorial before going into a theoretical model, or I guess a more rigorous model of what LMP pricing means, and then go through our transmission structure recovery, this market recovery algorithm, I guess, and then present a brief sort of toy example and look at some empirics and how this might be applied to other markets. The Midcontinent ISO, or MISO, this is this big green blob. So there's about 10 deregulated wholesale markets in the United States and Canada and North America, each of which allocates energy from large producers, from wind to coal to nuclear, those the actual generators of electricity, and they both operate the transmission network and facilitate markets which with various pricing mechanisms, and there's a lot of variation in the individual rules, so they allocate this energy to large utilities and also large industry as well. So the Midcontinent ISO is located, logically enough, in the middle of the continent. And it's this green blob here, and is one of the larger deregulated wholesale markets. I think it's the second largest next to PJM and has some 40 million consumers that are within that footprint. They facilitate a variety of markets. A day-ahead energy market, which is where the majority of energy is is decided upon. So that takes place at 11 a.m. each day. People submit bids, and based on that, both the demand and the supply side submit bids, and the electricity is, and a commitment is made to supply energy at those prices the following day. In addition, there's a balancing market. So if your demand happens to be a little higher than you anticipated, you're able to buy on a real-time energy market. And then there's also the ancillary services market, which basically provides reliability. So various generators can commit to being available, basically, if required. And then there's also a transmission rights market. And there's some interaction between these markets. And so anyways, so we'll be focusing here just on that pricing mechanism in the day-ahead energy market. And this pricing mechanism is a locational marginal pricing mechanism. So what does that mean? So first of all, LMPs are used by the majority, I think some 60% of people in North America are in the footprint of markets which use LMPs. So MISO, PJM, ERCOT, CAISO, which is Midwest, sort of the Northeast Seaboard, and Texas and California all use this sort of pricing now. And this is a relatively recent occurrence in the last 5 to 10 years, where they replaced zonal pricing, which was essentially what Ali was talking about yesterday, which is where you've got these uniform price auctions over specific geographic area. So basically a multi-unit auction over a specific area. The LMP mechanism works as follows. Participants, both on the demand and supply side, submit bids, which can consist of usually a marginal cost curve for specific either consumption or generation of electricity. The facilitator, in this case the ISO, MISO, will find, and I put in quotation marks, the welfare maximizing allocation, which is trying to, which is assuming that those bids are actually reflect costs and utilities of the participants. And so, yeah, and because it's not a cost maximizing allocation, because there's also elastic supply, or elastic demand in these markets. Right, and so then once they've got this allocation, they can ask the question, how much would it cost to supply an additional megawatt at a particular location in this footprint? So the price at a location is just the marginal cost, how much would it cost to supply an infinitesimally small unit at a particular location. Or another way of thinking of it is it's the dual price of that, of some constraints in that allocation mechanism. So this is quite different from a uniform price auction in that we have a very fine granularity of prices. Prices reflect losses, so some energy is lost to heat as it travels over the lines, so you can protect, depending on whether you're in North Dakota or in, right outside Indianapolis, the amount of losses will be quite different. And prices also reflect, where the energy can actually be used. So if it's windy and you're up in the North Dakota, then your price is likely to be low. You're in a high, but especially if there's constraints which limit the flow of that energy to higher population centers. All right, so prices reflect losses and active transmission constraints. This picture here is a particular hour, reasonably high demand hour at 3 p.m. On November 25th, 2013. And the prices vary. You can see in the southern area here where it's highly congested, the prices vary between negative $10 and positive $200 depending on a very short distance. Basically, we can assume there's some, we expect that there's some active constraints over here and active constraints over here which aren't allowing flow from these areas where there's very low prices. The other thing I just want to emphasize here is that just because you're in this blue area at this particular time doesn't mean you're going to be in a low-priced area all the time. Okay, so as different constraints become active, you can shift. There's a lot of uncertainty as to whether you're in a high-priced or low-priced area due to transmission constraints. So this picture just shows. This is the 5 randomly selected generators, and this is their distance, the price they're receiving, the price they're receiving from the hourly mean price. And I just want to point out that there's a lot of variation in who's receiving those higher prices. And yeah, part of this is due to bids, but a lot of it's also due to we believe it's due to transient transmission constraints that become active. So these transmission constraints, as they become active, they affect the structure of the market. So, we believe they also affect the market power in ways which may affect how participants behave. But unfortunately, these transmission constraints aren't fully observable. It's difficult to understand how, or it's due to actual legislation, such as the Critical Infrastructure Information Act of 2002. There's limited visibility into how a particular node is affecting a particular transmission line. And this makes equilibrium and counterfactual analysis difficult. And Ali alluded to this yesterday, that LMP markets are hard to do the type of work in electricity markets which has been done in. So some important empirical work. Bornstein, Bushnell, and Wallach looked at how much market power is actually costing in the California energy market, and that relies on identifying the efficient outcome, which obviously depends on transmission constraints. And so in a highly congested market, you need to have that information. The optimality of bidding behavior, or taxon puller, you need to have that residual demand derivative. And looking at comparing counterfactuals and what would happen if we changed the mechanism in some way, if we change that pricing mechanism. So Mara Regant has a new paper that's coming out that's looking at how increasing the expressiveness, basically, of bidding can result in, can change the. Yeah, and I guess another point is, okay, this is important for us as economists that want to understand and have limited access to data, but who else does it matter for? Well, I've had a lot of interest from people that operate in actual energy markets, and certainly, yeah, there's operational information here that could allow that can affect how people behave, and is difficult to get at through other means, statistical means. All right, so basically our research question is just that, can we get at this? So the transmission network's unobservable, but there's a ton of information out there. There's a ton of data out there that's considers both the pricing and allocation data on an hourly basis for these markets and at particular nodes. And the question for these, so basically the question we're trying to answer in this particular setting is, can the structure of this transmission constraints and losses be recovered from this pricing and allocation data? The broad theme, I guess, so I'm currently sort of wondering whether, and certainly would take feedback on this, whether there's applications beyond electricity markets and other efficient markets. And looking at identifying how those prices are come about from pricing and allocation data. Okay, so with that, I'm going to move on to actually talking about how this market functions. So I don't know how much people know about how electricity flow works, but certainly it's quite different from, say, a communication network, in that we have, as a network designer, you have limited control over where particular electrons flow. So it relies on Kirchhoff's law. And as a result, we can simplify sort of the network, essentially abstract out the network aspects of the problem and consider a linear, well, this is the linear approximation that markets actually use. And essentially it's a straightforward assignment problem where there's a set of public resources that, and depending on where you are in the market footprint, a generation of a particular 1 megawatt is going to have an affine effect on the usage of that, on the amount of available capacity at that particular, over that particular resource. So a transmission line would be this public resource, and the usage of that resource is locational, and it's, and we can approximate it using a linear constraint. So the model here, there's these 3 elements. One, we've got the set of participants who are, of course, generators and consumers. They're allocated some amount of production, xj. If it's greater than 0, they're generating. If it's less than 0, they are consuming. So it's just a symmetric model. We've got a set of locations. So each of these generators is at a particular location in the network. These are buses in the actual network. And at that particular location, you can sum up all, essentially they're able to trade without any sort of impact on the transmission lines. But the net production at that particular bus will have an impact on the transmission resources. So then we've got these transmission resources, and they've got these 2 sets of parameters. They have a capacity, little d's, and they've got a locational utilizations, DRI. So basically, that says that if you produce or say 5 megawatts at location I, then the amount of capacity you're going to use on resource R is DRI times 5. Okay, so if that's the net production, that's what you get. So a fairly simple set of constraints. We have the net locational production, just the summing up, getting that net locational production. Then we also have we use the same format for losses that is used in the MISO electricity market, where each location is assigned a loss parameter. So this loss parameter says for each megawatt you generate, what is the proportion of electricity that's lost to heat? And the market has to clear, so the sum of all the consumed energy has, so the sum of all the energy netting out the losses has to be equal to 0. And then the final thing is that, and this is what we're really, well, we're interested in those delta i's, and we're also interested in getting at these the d's and d's, but transmission has to be feasible. Bids are received from each participant. We have these, the bids have 2 parts. They've got basically a domain, the bid has to be between L and U, and then they also express their total cost for supplying X megawatts. So the allocation problem is to minimize the total, announced cost of producing, of satisfying all those bids. And then we've got that set of those 4 constraints. That first of all, that the net utilization, the market clearing, the feasible transmission, and then that each allocation is within the bounds put forth in the bids. Now, so what's the outcome here? It is the allocation, so X, and the LMPs correspond to the dual prices of the net production constraints here. So they're equal to negative pi. And that's the basic mechanism. So each hour, these bids are submitted. This optimization problem is solved over a large network with some. So in MISO, it would be about 700 locations. and on the order of 700. And then they're allocated the optimal allocation and given that program, and at those prices, negative pi. Okay, so that's our pricing mechanism. So what are we interested in doing here? So we know this form of the optimization. We have that information. And we know the partial, primal, and dual solutions. So MISO is also kind enough to announce this row here, which is essentially the transmission price. So in a competitive market, that would be the price that would be paid to a particular transmission line. So they announced those 3 pieces of information. And we're interested in recovering the parameters of the transmission constraints as well as the losses in order to build this mechanism again so that we can do some experimenting. OK, so we took some inspiration from the inverse optimization literature, which essentially, given a partial specification of an optimization model and a solution, which we've got there, use the optimality conditions to specify a feasible set of or a consistent set of missing model parameters, and then select from an appropriate representative from that set of parameters. So this was, pioneered in the 90s, and generally the problem that was approached is to look at inferring cost parameters. And so our problems, and it's been looked at with not only in linear context, but also in integer programming and conic programming and a number of other trickier combinatorial problems. So our problem's different from this, the classical problem in that we're looking at inferring parameters of the feasible set, so that what allocations are permitted. There's some overlap with other inference and networks. Won't go through this in detail, but people are trying to understand network topology from outcomes. There's also some overlap with use of constrained optimization in other structural estimation problems. And Chailin Su, who's here with Ken Judd, advocate, as a much more efficient mechanism than other algorithms to take advantage of mathematical programming software and explicitly representing equilibrium constraints in a mathematical program. All right. So to get at that information, it's a fairly straightforward process. We go to our optimization textbook. These are the set of KKT conditions. We look through those for one that has our relevant parameters and build ourselves a hopefully linear system that we can solve. So that's what we're going to do. The stationarity condition here reflects the locational utilization variables. And from that, and so we can build this. So we've got this system of equations, which has a couple little problems. One, the system's, in particular, that it's not linear because we've got loss multiplied by this unknown variable, which we don't, phi, which both unknown and we're not particularly interested in it. So we can take advantage of the fact that the original problem is overspecified, and so using the market clearing condition, we can figure out the production at any, if we have production at n-1 buses, we can figure out the production at that last bus. So we can set a reference location and select an arbitrary location R, which is basically an arbitrary location R. And for all of those R's, we can set their utilization parameters equal to 0. So then the D that we are going to infer is going to be relative to that reference location. But it will matter which location we choose, we're going to get a effectively the same set of, we're going to get an equivalent set of constraints. That allows us to, to express phi as equal to this, this price, the price at that location over its loss, its relative loss, and we can specify these relative loss parameters, Qi equal to the, where the loss is relative to that reference location. So using that, we can build this set of linear equations where we've got the locational utilizations and these relative losses, and the only information that's required is both the LMPs and the transmission prices. Okay. So then we got that system. And so basically our algorithm is just to take advantage of that by, so we select that reference node, set all those things equal to 0. We get that system of equations. If we have enough samples with the same, or with an appropriate subset of active constraints, just note, if a constraint isn't active, you don't have any information about it, because its shadow price is equal to 0. It's not affecting the outcome in any way. So that gives us the set of linear equations. If we've got enough samples, we're able to solve that, assuming the system's of full rank. And then we can recover the transmission capacities from allocation data. So yeah, so just quickly, so what are we able to do here? We've got, so if we have R+1 samples where R is equal to the number of active transmission constraints, which is a fair, there's on average maybe 7 or 8 active transmission constraints. Or not on average, at the most there's about 7 or 8 active transmission constraints. Most of the time there's 1 to 4 probably. Then you can identify the relative losses and D for the active constraints. If you also have the allocation data, then you can identify the capacities for those active constraints. And using those 3 pieces of information, we can just replace the market clearing condition with the losses there with the locational losses, and you can reconstruct that pricing mechanism using those constraints. So as I said, we've got a lot of data with respect to Midcontinent ISO, and so and in that data we can see the transmission prices, which tells us which constraints are active on a given hour. So we took a look at several test sets where there's 1 to 3 active constraints, and I should say, so we by identifying, we found a bunch of samples. Not identify anything in them yet, and we sort of so for each of these examples we had 3 sets of samples to do some in-sample and out-of-sample testing, basically, to see how effective we are at actually regenerating that pricing mechanism. So in the in-sample, these are the samples that were used to actually recover those transmission constraints and losses. In the out-of-sample set, where those are hours where the same set of constraints is active, but those aren't, they weren't used to generate. So there's some differences in the actual in the bids for those. That information was not used to generate the in-sample, so the prices are different. And then we took a look quickly at when we have well out of sample, when we have active constraints which aren't a subset of the in-sample constraints. So hopefully, our hope was that we would be able to do reasonably well, or very well in the in-sample, pretty well in the out-of-sample, and then actually have bad predictive power on the well out-of-sample stuff. Okay, so we recover D, D, and Q using the in-sample, and then that gives us the following sort of pricing, estimated or recovered pricing mechanism. And then, so we ran that, and I'll just go through these one by one. All right, so basically, I just want to point out, so we looked at a few objectives here, or measurements here. I guess the correlation between the prices. So if we've got high correlation, then we're doing a good job at predicting them. And we looked at the average absolute error, both for the prices and the megawatts of generation. We did this for both the full set and for if you remove the 3% of outliers with large absolute error. And the reason we did this is, so on the next page, is what we found is we had some systemic error, which, when congestion's low, we were able to come up with a pricing mechanism which is slightly shifted. It's a little low, but it clearly reflects the actual prices very well. Now, if we looked at, if you got rid of those, the outliers here, you'd see that this has, these two subsets have a similar correlation. They're nice straight lines, but they obviously, there's some systemic error there, which we believe reflects missing demand and supply data. So that's a bit of a problem, but we're looking at whether we can use this mechanism to identify imports and exports with, and other bilateral transactions with try and figure out what's actually going on there. So we have a very nice correlation there. We're doing a pretty good job at explaining the price variation, but there's limited demand and supply data. In addition to this, we estimated the residual demand derivative. So the residual demand derivative is a good reflection of the incentive of a particular player to shade their bid, to adjust their bid. So this is the transmission constrained residual demand derivative that can be calculated efficiently. Zumbaldic have a nice paper that shows you how to efficiently calculate this for a lossless market. And and as I said, it reflects these incentives, and it's locational, so it reflects incentives at a particular location as opposed to other market powers. And so that's just the actual supply function, that how the residual demand derivative would affect the best response in that supply function. And so it's been advocated in the EE community as the basis for effective, market power measures which that are more principled and can be used to and actually reflect transmission constraints and sort of the locational pricing power throughout the market. And so the drawbacks are that the efficient calculation doesn't take into account discontinuities in both, when does a new constraint become active, or when you're actually making your bids, you're concerned with, the probability of a particular, of you affecting that particular constraint and making it active if you're near it. And also, it doesn't take into account the discontinuous bidding function, but that's not too big a problem. You can smooth those bidding functions. So here's the actual. So we adjusted or adapted this for our market with losses, and this is the formula there. Just want to point out, so the components of that formula are the slope of the marginal cost, so the second derivative of the total cost, and the active constraints, so the parameters of the active constraints, the current active constraints, so they affect how easily power from one part of the grid can be moved to another part. And then the losses also play a role. And so those are the participant losses. And so we looked at this we calculated this for each location in the network, and or for each participant in the network. And so in our low congestion setting, we found it turned out to be a relatively compact set of residual demand derivatives between 0 and negative 18. And in the high congestion setting, there's a lot more variation. Still, most people are within that 0 to 20 area, but there are some bidders that have very high residual demand or high magnitude residual demand derivatives. And I just should point out that so calculating this residual demand derivative doesn't have the same problem with allocation data that our previous. It doesn't rely on the actual capacities of those transmission constraints. So we have more faith in this number than in our pricing numbers, I guess. Okay, so this just shows how those residual demand derivatives depend on particular constraints. So this is one active constraint, and where the active constraint doesn't have a particularly large impact. I've sort of cropped it a little bit, but essentially it's centered on 0. And there's one particular constraint which seems to be so that highly congested area is a high demand area, and there's high correlation between the parameters of that constraint and that residual demand derivative. Okay, so just briefly, I will have about 2 minutes, but so I guess my question is whether this, maybe I'd love to get some feedback, whether this can be applied to other commodity markets. So, so typical empirical explanation is that price differences are this in different areas are a linear function of a border and distance, and but in certain markets like the natural gas market, the price of natural gas in Japan is not just due to the fact that there's a border. It's due to the fact that there's a capacity, a liquid natural gas capacity that's being reached. So that price difference of between 2 and 3 times reflects not just a linear distance. It's because there's an active constraint. So if we have a competitive market with where we can argue that these dual prices will correspond to a similar optimization problem that we looked at there. Right. So basically, if we can at least approximate that resource that constrained transportation technology by the usage of that technology by affine locational utilization for shared capacitated resources, and argue that it's being allocated in an efficient manner, then we may be able to extract some of that structure in a similar way. Okay. So we looked at that methodological question and identified a tool for optimal efficient markets with system-wide capacity constraints. And there was some empirical value there in being able to identify loss in resource utilization parameters, reconstruct that allocation and pricing mechanism, and identify the residual demand derivative, which is certainly of interest to economists and hopefully also interest to market participants who face the same sort of unobservability that we have. And then, we're interested in using this to actually understand how consumers or our participants are changing their behavior based on the varying market conditions in these markets. Okay. Sorry. Yeah.
So actually, I'm very confused about the way you formulate line constraints here, right? So this is big matrix D multiplied by D and D.
Yeah.
So you're assuming to know nothing about the network topology whatsoever.
Yeah, so you don't need to know the connection. So,
but then when you say you're using like transmission price and presumably residual financial transmission prices to identify which constraints body.
Not financial transmission rights. Actual transmission. No, they so that dual variable, the rho, is which is not the FTR price. It's an announced price that it's announced in order to sort of give people information.
Fine, but when you say you identify the constraints binds, what does this constraint, right? Because now you don't know the network topology, so you can't. It's the mysterious part. When you say, right, I've identified the.
So do you want to? So you're saying, sorry. So you're wondering how can you get to?
There's no one price. There's a price differential. Something must be. Some constraint is fine. Right? And that's because
Yeah,
first
yeah.
location, and then
I mean, part of that's also due to losses, but
Somewhere some constraints defined.
so yeah. So actually, identifying individual, I guess reconstructing the grid topology is then another step. So I mean, so I tell in the paper there's an appendix which just shows that how that you can move from a grid topology with line impedances and whatnot to this sort of locational utilization, sort of linear affine model. But going back in the other direction is not as clear. I'm not. Yeah. Because if you knew the whole net, you'd need to identify, I think, every constraint in the network, or every transmission resource in the network, and then you may be able to do that. Any other questions before we move on to our other empirical talk? All right.